And converting phase 1 into phase 2 is very easy. The configuration of the hub is gonna be the same as in phase 1, so we don't have to change anything on the hub, but on the spokes we change the tunnel mode from the default GRE IP to GRE multipoint. So the tunnel can be terminated at multiple destinations, which makes it possible to establish dynamic spoke-to-spoke tunnels. So the traffic will go directly to the other spoke without touching the hub router. Show running config interface tunnel 0, and this is the configuration of the tunnel interface of spoke 1. We are going to remove the tunnel destination, so no tunnel destination, and change the tunnel mode GRE multipoint, and we do the same on spoke 2 and spoke 3 as well. So now we have phase 2, and let's take a look how it works. I'm gonna start a packet capture on this link and on this link, and we are going to do a trace route to spoke 1 from spoke 2, or trace route 10.0.0.1, and as you can see, the first packet goes through the hub. But if I issue the command again and again, any subsequent packet goes directly to spoke 1 without going through the hub router, because show IP NHRP, this address is now in the local NHRP cache. With the help of the hub router, spoke 2 resolve the NBMA address of spoke 1. And here is the mapping of the NBMA address to the overlay address. And it's valid for 2 hours by default. So first, spoke 2 sends a resolution request to the hub router. Here is the NBMA address of spoke 2, and here is the tunnel address of spoke 2, and he wants to reach 10.0.0.1, which is the overlay address of spoke 1, and he's asking for the NBMA address of spoke 1. So what does the hub router do? The hub forwards this request directly to spoke 1, and spoke 1 responds back directly with this NHRP resolution reply, saying that here is my NBMA address 192.0.0.1. So this NHRP resolution reply goes back directly to spoke 2, and spoke 2 now has the overlay to underlay mapping in his NHRP cache, so that now he can reach spoke 1 without using the hub router. And now let's enable routing on the overlay, and we will start with EIGRP. So with routing in phase 2, we have one important thing to remember, the next hop address in the routing table must point to the tunnel IP address of the spoke router, not to the hub router. So this restriction does not allow us to perform summarization on the hub router, so we couldn't just create a default route on the hub and advertise the default route towards the spokes. That won't work in phase 2. This will be possible in phase 3, but in phase 2, the spoke is who initiates the spoke-to-spoke tunnels, not the hub. So the next hop address must point to the tunnel IP address of the other spoke. So I quickly enable EIGRP on the loopback interfaces and on the tunnel interfaces on all routers, as I did in the phase 1 video, and we will see how we have to modify the default configuration. And again, there is adjacency between the hub and the spokes. There is no adjacency between the spokes. So let's see the routing table of the hub. And just as expected, the hub has learned all routes from the spokes, but the spokes have only learned the route of the hub. This is because the split horizon, what we have seen in the phase 1 video. So let's turn off split horizon on the tunnel interface, interface tunnel 0, no IP split horizon, EIGRP, and now if I issue the command again, the spokes could learn the routes of other spokes, but the next hop address still points to the hub router. So if I run a trace route to spoke 2, the traffic goes through the hub, and not just the first packet. Any subsequent traffic will also go through the hub, which is not the desired behavior of the phase 2 DMVPN. So let's change the next hop on the hub. No IP next hop self, EIGRP 100. Here is the EIGRP update, which the hub sent to spoke 1. Here are the prefixes, and the hub preserves the next hop of the advertising router. For example, this prefix 2222/32, the next hop points directly to the tunnel IP address of spoke 2. And now the routing tables should also reflect this change. I'll do show IP route. Yes, so the next hop now points to the advertising router. So if I perform a trace route to spoke 2 again, the traffic goes directly to spoke 2. So I quickly remove the EIGRP process from each router, and we take a look at OSPF. and I enable OSPF on the loopback interfaces and on the tunnel interfaces. And we put everything in area 0. And in phase 2, we have to use the broadcast network type on the tunnel interfaces. Because as we have seen in the phase 1 video, the point-to-multipoint network does not preserve the next hop address. So in the case of point-to-multipoint, the next hop addresses would always point to the hub router, which is not what we want in phase 2. Instead, we are going to use the broadcast network type. And as I have said in the phase 1 video, we must be very cautious regarding the designated router election. The hub router must be the designated router, and we change the interface priority to 0 on the spokes so that they can't even participate in the DR election. So let's start with the hub, interface tunnel 0. We change the network type to broadcast, IP OSPF network broadcast, and we increase the priority, IP OSPF priority to 55, no shutdown. And similarly on the spokes, interface tunnel 0, IP OSPF network broadcast, and we change the priority to 0. The adjacency is up, so I'm gonna do the same on spoke 2 and spoke 3. And now let's see the routing table. And we have all the routes from the other spokes, and the next hop points to the advertising router, so not to the hub. So if I run a trace route to spoke 2, for example, the first packet goes through the hub, but any subsequent packet will be forwarded directly to spoke 2.